Hello everyone, I shall welcome you all for another session on free vibrations of undamped single degree freedom systems. Okay, in my last lecture I introduced you the energy method of analysis, and I also applied that energy method to a spring mass system and mentioned that I shall apply energy method to simple pendulum and also demonstrate you how we can obtain that. Okay, so this is the simple pendulum which I have mentioned, the simple pendulum of length here, this is what is length here, and this is point O, this is the mass M. Okay, we have point mass. The string is not having any mass. Okay? So now this is the equilibrium position, and I allowed it to undergo free vibrations, and I just move it here and leave it here, and then it is what is oscillating. It is undergoing free vibrations. This is at some instant of time, say t equal to t. Okay? So I have arrested in my eyes this position and want to analyze it. And one more thing I would like to mention here, for the sake of analysis, this theta or the amount of displacement appears to be quite large. But as you all know that we are assuming that theta is going to be very, very small. For that small value of theta, what is going to happen? That is what we are going to analyze. So in real sense, it is oscillating something like this, very, very, very small. But for my analysis purpose, I have shown it very, very large, as if, because I want to demonstrate something, and so that value you will be able to see it with your naked eyes. Otherwise, you won't be able to find that. That's why, with that intention. So though I have shown theta quite large, please remember our theta is going to be very, very, very small. Okay, this is the position. This mass is having energy. Okay, I would like to calculate what is the energy. The energy may be in kinetic energy or potential energy. So I would like to calculate what is the total energy possessed by this system in this situation at this instant. So I know that total energy is the sum of kinetic energy plus potential energy. Okay, I also know that kinetic energy may be in the form of translation or may be in the form of rotation. So in my system, is there anything which is sliding, which is moving along a straight line? I don't have. So I have a mass which is undergoing motion like this, that is nothing but the rotation about this point. So the mass is undergoing the rotation about point O, and therefore I have kinetic energy because of rotation. I don't have any translation. Okay, I don't have kinetic energy because of translation is 0. Then potential energy, I don't have spring here. The potential energy is only because of the change in the position. The potential energy because of position. So I don't have any potential energy, any energy due to which is stored in the spring, because I don't have a spring here. Okay, now it's very simple now. Kinetic energy because of rotation. In general, it is half I omega square. Okay, half as it is half. Okay, I is nothing but I naught, because the rotation is about point O into what is omega? Omega is nothing but theta dot square, plus potential energy because of position. What is the potential energy? Okay, so the mass has, with respect to the equilibrium position, it has come here. So first you decide whether the potential energy, is there a change in the potential energy with respect to the equilibrium position, is it positive or negative? Okay, so it has gone up. You all agree, no? The earth center is below, and with respect to the earth center, it has moved away, and therefore the potential energy is positive. That is the first thing. Okay, then what is the potential energy? The first term you can write it mg as it is, multiplied by what is h. What is h? With respect to the equilibrium position, so this value, this is what I mean by h. Okay, probably this value, this is what I am interested in. This I can say that this length minus this length. So therefore, what is this length? This length is L. And what is this length? As you all know that this is L and this is theta and this is L cos theta. So therefore, L minus L cos theta. This is the potential energy. So therefore, this is equal to half as it is. So what is I naught? I naught is nothing but ml square. I have a point mass. The moment of inertia of this mass about 0.0 ml square into theta dot square as it is theta dot square plus mg into L also I shall take it outside into bracket 1 minus cos theta. Okay, this is what? This is total energy. Total energy is equal to so much. Or fine. Now what is to be done? Differentiate this d by dt of, what is the meaning of this? The rate of change of total energy. The rate of change of total energy. As we all know that total energy doesn't change, total energy is always constant. This is equal to 0. You can start with that and differentiate this. Please remember, we are not differentiating these terms with respect to theta, we are differentiating with respect to time. That you remember. Okay, so the first term as it is half ml square, this is a constant. Then differentiation of theta dot square. First I shall differentiate this theta dot square with respect to theta or theta dot. That is nothing but 2 times theta dot. This is the differentiation of this with respect to theta dot. Now you differentiate theta dot with respect to time. That is nothing but theta double dot. That is nothing but d square theta divided by dt square. Okay, that term is over plus this side. It is mgl. So now I am supposed to differentiate with respect to time. The first term is 1, which is a constant. Differentiation of 1 with respect to time is 0. Forget it. Now minus as it is. Then but differentiation of cos theta. First differentiate that cos theta with respect to theta. What is that? That is minus sin theta. So this minus is as it is. This minus is because of the differentiation. Okay, sin theta, differentiation of cos theta with respect to theta. Now I have to differentiate theta with respect to time. That is d theta divided by dt. What is d theta by dt? That is theta dot. Theta dot. Okay, so therefore now simplify this. The left hand side is 0. This is equal to maybe this is 2 and 2 I shall cancel. Okay, here it is alright. Okay, I shall expand it now. So as you can see here, divide throughout by theta dot. Though I have minus sign here, the whole thing is bracket. So therefore this into this. Okay, so I can divide throughout by theta dot. 0 divided by theta dot is 0. Theta dot by theta dot, it will vanish. Theta dot divided by theta dot. Now what is remaining? And probably here I have L square, here I have L. I can divide throughout by L. 0 divided by L is 0. So ml square divided by L is nothing but L. So it is as one L goes and one L goes here also. Okay, ml, what is remaining is ml theta double dot plus. Okay, minus into minus plus. What is remaining here? mg into sin theta. This is mg into sin theta. Okay, for small theta, for small values of theta, this is the meaning. For small theta, what happens? Okay, let me write on this and then equal to 0. So m into L into theta double dot. I can cancel m also. I can cancel m also, which I forgot. I could have done it here also. So no problem. So what is remaining? It is L into theta double dot plus G So once theta becomes very small, very small, what happens to sine theta? Sine theta becomes theta. It is not 0, it is theta, which is equal to 0. Rewrite it, theta double dot plus g upon L into theta is equal to 0. So therefore, I can write easily what is omega L? Omega L is root of g by L. I hope it's clear. Okay. So this is how the energy method. Whatever the method you apply, the final expression will remain same. The method of analysis is different. So these are various methods what we have gone through, and we usually apply any of this method. If the system is quite complex, in that case we may go for energy method. If the system is very simple to understand, analyze, then we may go for the Newton's second law. So usually they don't mention what method you need to employ, but you should know all the three methods. Okay. So the next method, the fourth method, which has been mentioned, and since it is mentioned in the syllabus, I shall also discuss here. I am not going to spend much time because normally we don't apply this method for analysis, and since it is mentioned in the syllabus, I shall also discuss it, and I don't intend to spend too much time on this. The other method is what is called as Rayleigh's method. This method does not get you the differential equation, it will get you straight away the expression for the natural frequency. It will get you straight away the expression for natural frequency. Okay, I can say finds expression for omega n without finding a differential equation. This is the specialty of this method. But all those three methods which we have understood so far, all of them will get the differential equation, and we make use of that differential equation and then find out. Okay, so we also assume or make that solution of motion, that means differential equation. Solution of motion is simple harmonic motion. That is what we have to assume. So we have simple harmonic motion, and that is the assumption. Okay, so what is simple harmonic motion? As you all know that x is equal to a sine of omega t or omega t plus phi, a sine of omega t, and if that phi is 0, then I don't write it, or in general a sine of omega t plus phi. This is a general expression for simple harmonic motion. What is x? Okay, I may also have instead of x, if I have theta. Theta is the displacement. Then usually a is replaced by beta, because the amplitude also is in terms of the angle now. So beta is the amplitude. Then sine of omega t plus phi. It may be like this also, depending upon what motion you have. If it is linear motion, then we use this. If it is an angular motion, we use this. Okay, so now I shall continue. I shall explain the remaining part, taking only any one of them. Say this one. I shall differentiate. Let me differentiate this with respect to time once. X dot. What is x dot? X dot is basically dx by dt. You agree now? Dx by dt. What is dx by dt? X is displacement and t is time. What is this? This is velocity. So x dot is nothing but velocity. What is x dot? Differentiate this. So I think I can straight away write it a into omega into cos of omega t plus phi. Alright. So a as it is, differentiation of sin omega t plus phi is cos of omega t plus phi. Differentiation of omega t is omega. So a into omega. Okay. So from here, I would like to write down what is V max. What is the maximum velocity? Or in other words, what is x dot maximum? How much is that? That is equal to a into omega. And what is A? A is amplitude. Please remember, A is amplitude. Multiplied by what? Multiplied by frequency. That is natural frequency. Please remember, this is very, very important. So the maximum velocity is amplitude multiplied by frequency. Okay? So this is equal to, we may write it for free vibrations, this becomes A into omega n. I hope you understand. Okay, then, so what is A? Please remember, A is amplitude. A is amplitude, omega is frequency, and phi is phase difference. And omega, for free vibrations, I am going to denote it by omega n. Omega suffix n, nothing else. I hope it's clear. Okay. Now, before I go to this method, okay, I have something what is called as potential energy. In general, what is potential energy? Potential energy, it may be mgh. It may be plus or minus. Okay, then what is called as energy in spring. Energy in spring. Energy in spring. So this is potential energy. And what is kinetic energy? Kinetic energy, as you all know, is half m into x dot square. And if you have translating motion or motion along a straight line, or if you have rotation, then you have half I, moment of inertia about an axis about which the rotation is taking place, into theta dot square. Please remember this, and this I shall keep it here and then come back to this method. Okay, what is Raleigh's method? So Raleigh's method makes use of what is called as the energy. Okay, so now when I have a system which is undergoing free vibrations, okay, I have continuous change in potential energy and kinetic energy. At any given instant, the total energy is the sum of the potential energy and kinetic energy. If the kinetic energy, as I said, total energy is equal to kinetic energy plus potential energy. Do you agree that if kinetic energy is 0, if kinetic energy is 0, then total energy is potential energy, and that potential energy is maximum potential energy. Okay, if this is 0, then this has to be maximum, equated to this. Similarly, if the potential energy is 0, then kinetic energy is maximum. Understood? If kinetic energy is 0, potential energy is maximum. If potential energy is 0, then kinetic energy is maximum. So in this Raleigh's method, what it does is equates the maximum potential energy and the maximum kinetic energy are equated. And that is how we get what is called as the expression for the natural frequency. Okay, you have to identify at what position of the vibrating system you have maximum potential energy and at what position you have maximum kinetic energy, and make use of that and write down the expression. Okay, I shall apply this now. So what is Raleigh's method? What does it do? This does maximum potential energy is equal to maximum kinetic energy. This is what is done in this method. Okay, now I shall apply. I shall take what is called as a spring mass system. So I shall draw a smaller system. Okay, smaller diagram. Okay, what is this? So now there is no length, no load on the spring, and the spring is of stiffness K, and this is the the free length of the spring. The spring has not undergone any extension. Okay, so now I attach a mass. The moment I attach a mass, I know that the spring will get extend the spring shall extend, and the mass will come here, and this I have called it as delta ST. Now all the methods I have shown you, delta ST, and I know that this is mg divided by this value. Okay, this position I have called it as, this position of the mass I call it as equilibrium position. This is my equilibrium position of the system. Now I induce free vibrations. How? I pull this mass up to here and leave it. And when I leave it, there is no force acting on the mass, but the mass will not remain stationary in this position. The mass will go back to its equilibrium position, crosses that equilibrium position and goes to the other side, one extreme position. Then again comes back, crosses equilibrium position, and this is what will go on forever because the system is undamped system. And therefore, okay, this is going to oscillate continuously. This is going to oscillate continuously. Let me assume that the one extreme position of the mass is somewhere here. Please remember again, I am showing the amplitude. This is what we call it as amplitude. For the sake of understanding, I am showing it quite large. You are not going to have that much large value of amplitude. The mass may be oscillating somewhere here. Your naked eyes may not be able to identify. So this is one extreme position. Maybe at the side you have another extreme. The mass is moving. This is the equilibrium position starts. Okay. So when it is going down, do you agree that its velocity is increasing? The velocity is increasing or velocity is decreasing? It has to reach here, and by the time it comes here, what will be its velocity? It is going down. Then it is changing its direction again. And do you agree that the velocity is 0 here? The velocity is 0 here. Then it is moving in this direction. Its velocity is increasing, comes to the equilibrium position. The velocity is maximum. Now the velocity starts decreasing, and by the time it comes here, the velocity is 0 here again. And at this, we have the maximum velocity. The maximum velocity occurs at the equilibrium position. Understood? The maximum velocity is at the equilibrium position. And what is the potential energy? Say either here or here when it comes to this position. So the maximum potential energy has increased, it is positive, and the potential energy, the energy is also stored in the spring. The energy is stored in the spring, the energy is changed because of the position of the mass, and therefore I have to calculate what is the net total energy, potential energy at this position. When the velocity is 0, potential energy is maximum. And by this position, what is the potential energy? Since it is the equilibrium position is the reference and the mass is at the equilibrium position only, and I don't have any energy because of the position, and the spring also has not undergone any extension, or it is here only because of delta ST, and therefore the potential energy, that what I mean is the energy stored in the spring is 0. So potential energy is minimum here, kinetic energy is maximum, and here or here the kinetic energy is maximum. The potential energy is maximum. This is what I am going to use. Okay, so Raleigh's method, maximum potential energy and maximum equal to maximum kinetic energy. So let me calculate what is the maximum potential energy. Maximum potential energy. So anything, this value or this position, it doesn't matter. Okay, so what is the potential energy? Potential energy, let me take this position and find out. So the mass has come down, therefore its potential energy is minus mg multiplied by this distance. What is this? This distance is, remember, it is amplitude. Okay, so let me call the amplitude as A. A as the amplitude. Okay, minus mg into A. You all agree now? Minus mga. Okay, plus. Okay, then the energy stored in the spring, that is nothing but the average force during this time multiplied by the displacement. So what is the average force? What is the force in the spring at this position? What is the force in the spring at this position? That is nothing but K multiplied by delta St. And what is the force in the spring at this position? That is nothing but K plus K into delta St plus amplitude. This is divided by 2. This is the average force. This is multiplied by the displacement. What is the displacement? Displacement also is equal to A. Okay, I hope you understand. Okay, this is equal to what is the kinetic energy? What is the maximum kinetic energy which occurs at this position? And I have kinetic energy only because of straight line motion along a straight line, which is equal to half m into velocity maximum. Okay, velocity maximum square. Maximum velocity. So earlier so velocity in general is equal to A omega, or velocity maximum is equal to A into omega. This is what I had showed you just now. So when I discussed, so x equal to A sine of omega t plus phi, differentiated x dot, this is equal to A into omega cos of omega t plus phi. So when this is 1, x dot is maximum, that is equal to A into omega. What is this A into omega? That is amplitude into this. Amplitude into frequency. So this is what I am going to use. Okay, let me simplify this. Minus mga plus k into delta st plus k into delta st. 2k delta st divided by 2. That is nothing but k times delta st multiplied by A. Okay, so then I have one more plus k into A, that is k A square divided by 2. This is equal to half m velocity, that is nothing but the amplitude into omega n whole square. Correct? Yes or no? Velocity maximum is equal to A into omega n. That's what I have substituted here. So when it is here in this question, what is the velocity? Maximum velocity, that is equal to A into omega n. So simplify this. So we know that k delta st is equal to mg. K into delta st is mg. K into delta st is equal to mg, and therefore this and this cancels. So what is remaining here? Half k into A square is equal to half m into A square into omega n square. So half 2 cancels. Okay, A square and A square cancels. You keep omega n square here only and bring this m this side. It becomes k by m is equal to omega n square. Therefore, omega n is equal to root of k by m. This is the expression for the natural frequency of a spring mass system which we have obtained. Please remember, I calculated the maximum potential energy at this position. Even if you take this position and do it, you will get the same expression. The slightly there will be change. This will be plus, there will be a minus here something, and you will get finally the same thing. Okay, Raleigh's method therefore gives you natural frequency straight away without getting the differential equation. I hope you understand. Okay, so I want you to apply Raleigh's method for simple pendulum also and get that. Okay, if you have any difficulty, approach me. I can solve it in my next class. Okay, all the best. Thank you.